We'll give everyone a few more minutes to gather up here. We've got people joining us. We'll wait till that slows down a bit. We'll go ahead and get started here a few minutes after the startup time, but I want to welcome everyone to our second in our virtual tutorial series. This one's going to be concerning the open source data tools and open access solar data. And this is all related to the Solar Data Bounty Prize that was issued out recently. And our last video tutorial series last week concerned with accessing the data and downloading the data. And so we're going to continue on in that vein today. Mike, you want to go to the next slide?
Whoops. There you go.
So the idea was that we wanted a lot of the PV fleet owners out there to allow the public to get access to some of their data sets from operational PV fields. And we're hoping that this high quality data sets will allow additional development of algorithms and studies in an effort to understand what's going on in these plants and how better to improve our production of electricity through solar means. We are hoping that the academic industry and students out there will grasp onto these data sets and these analysis means and extend them forward into the future. Next slide, please. So you can see there are 3 webinars here. We're on the second one. We're analyzing system performance. So we're going to go into a look at PV analytics, RD tools, and the solar data tools. And to start us off is going to be Kevin Anderson from Sandia Labs. So take it away, Kevin.
Thanks, Robert, for that intro. Hi, folks. So like Robert just said, we're going to be looking at 3 different software tools today. All of these are open source packages and freely available to the public. They're also all written in the Python programming language. And in particular, since this is the second webinar, they're all focused on one or another type of time series analytics. And so these are all going to be extracting knowledge from measured data. And just to plug the third webinar on Thursday, those will be looking at the modeling tools, PV-Lib and SAM. So there's going to be 3 tools talked about today. The first one is PV Analytics, which is a library focused on data pre-processing and quality assurance. This is a nice, it's designed as a toolbox of functions along the lines of PV-Lib Python, if you're familiar with that tool. And it's more of a foundational package to build other projects on top of. So the idea here is that many different data analysis tasks in the world of PV require similar data pre-processing and QA attention, things like filtering out erroneous data points, identifying problematic data periods or aspects of system performance that you don't want to include in a particular analysis. And the idea is that PV Analytics brings all of these different pre-processing methods into one place so that all these other tools don't have to reinvent the wheel and do it themselves. So it's really easy to install this package. It's really easy to install all the packages, but this one is available on the Python package index. You can pip install it like any Python package. And here are the links for the documentation and the GitHub repository. Next slide, Mike. So just to briefly overview the functionality in the current release of PV Analytics, in terms of data quality assurance, there's a lot that can go wrong with outdoor field measurements, especially in commercial grade systems. And so the first major pillar of functionality here is about things like checking consistency between different measurements to make sure that, or rather to identify times when one measurement might be wrong relative to other ones. Things like identifying time shifts, daylight savings time, for example, is a relevant one these days, as well as capacity shifts in data. For example, if somebody misconfigures a meter halfway through its lifetime and it starts reporting in different units, PV Analytics can detect that easily, as well as filters for outliers and completeness scores. In addition to identifying potentially problematic data, it also has features for classification and labeling of normal good data, things like identifying day and nighttime periods just from the data itself, rather than based on a solar position algorithm or something like that, identifying clear sky conditions and inverter clipping. And there's a lot more that doesn't fit into either of those two first categories, things like calculating different indices, variability index, performance ratio, things like estimating system parameters based on its monitoring data, for example, its orientation and azimuth tilt, and other functionality like that, and is constantly growing in the future. Next slide, Mike.
All right. So thanks, Kevin. The second tool that we'll be talking about is RD Tools. Like everything we're talking about today, it's an open source Python package for PV time series analytics. I think the thing that distinguishes it from PV Analytics, which you just heard about, is that it's really built up around a few specific workflows, and we provide kind of a high-level interface to deploy those whole workflows in just a few lines of code. So the applications that we currently support today are degradation, which is the namesake of RD Tools, degradation rate, RD. But we've since added soiling and availability analysis, which will show you how those work. There's illustrations of them here on the slide. And we may add more in the future. So we're going to focus on these, but I just want you to keep in mind that even though we're not going to get into the guts of it, all of the bits and pieces are there available for you to put together your own analysis, so you can build up in a functional way as well. A little bit about the structure of RD Tools. This is a screenshot from our Read the Docs. So you can see here, if you look at the submodule layout on the left-hand side, the part that I'll be talking about is the analysis chains module. This provides a object-oriented interface to deploy the entire degradation analysis and the entire soiling analysis. Everything underlined in orange are the functional submodules that support that though. So that's where you'll look if you want to just like kind of excise one piece and use it for something. Then Kevin will be talking about the system availability module, which I've underlined in purple. And then we've got kind of a cross-cutting submodule for plotting things that touches various parts of the library. As just a few notes about the input data, typically we're looking at PV energy or power time series. And then we also do require irradiance and temperature. That's because most of the workflows are model-based in RD Tools. And then we can work at the inverter or the meter level. In fact, both are required for the availability analysis. Multiple years of data are required if you want to extract a degradation trend. Usually we're working with like 15-minute frequency data, but like it could be 5 or hourly. There's some flexibility. It is typically in that intraday, better than daily resolution. But the code will support other resolutions too, so you're welcome to experiment with things. And then just to note that under the hood, it relies heavily on the Python package pandas. So moving on, just kind of an overview of the workflow, that's what's going on behind the scenes when you see me deploy that trend analysis in the demo portion later. We start with that high frequency performance data, right? That's like that 15-minute or 5-minute or whatever power or radiance, power or energy time series. The first step is to normalize it to a model that we construct out of the irradiance and temperature. And it can be, you'll see me use satellite data and ground-based data. We can also use like clear sky model data for the irradiance, so it's a little bit flexible there. Anyway, once it's normalized to a model, then we filter out anomalous data points to kind of clean things up, and then we aggregate. And normally we aggregate to the daily frequency, which you can see all the way on the right-hand side of the slide here. And then that daily time series is what we actually analyze to extract degradation rate or soiling losses. You can aggregate to other frequencies too, though. if you're interested in something else, like we're experimenting with aggregating even sub-daily, or you can aggregate weekly if that makes more sense for your data set. This is just kind of the normal workflow. And again, that's going to be going on kind of under the hood when I use trend analysis later. So please keep that in mind. Back to Kevin.
Thanks, Mike. The third major analysis provided by RD Tools is looking at system availability, and I'll talk more about this later, but just to give you a little bit of a preview, the main challenge to be overcome here is in distinguishing true outage events where a piece of hardware is legitimately offline and not producing energy from mere communications interruptions where there has been data loss or data corruption that makes it look like a piece of hardware is offline. But this is just a data artifact, and in reality, the system was performing normally. So this is a non-trivial task to accomplish in practice, and we'll talk more about how RD Tools goes about solving this problem later on. So again, RD Tools is also available in the Python package index. Here's the command to install it into your Python environment, and here are the links to the documentation and the development repository on GitHub.
All right, and the third tool we'll be talking about today is Solar Data Tools. Again, like the other tools, this is an open source Python library for analyzing PV time series data. Specifically here, we're focused on analyzing power and irradiance data specifically. This package was designed with the goal in mind of analyzing what we call unlabeled PV data. So that is data where we don't necessarily have a site model or reference meteorological or irradiance data. Solar Data Tools has methods for data cleaning, filtering, plotting, and analysis. And unlike RD Tools and PV Analytics, it's not taking a PV system modeling approach to doing these analysis, but instead using a statistical signal processing approach to make the estimates of of system loss factors as well as operational issues. Additionally, the data processing steps are largely predefined and automatic, regardless of system type, from utility tracking systems to multi-pitch rooftop systems. The idea is to try to really reduce the amount of time from getting your hands on a new data set to getting actionable insight about that data set. We show a few of the outputs here that Solar Data Tools can create. I want to especially call out in the upper right corner, it has a very nice function to turn any power data set into a heat map, even if you've got arbitrary missing values or timestamps. Next slide, please. So you can find us most easily with pip install Solar Data Tools. We're also open source on GitHub, and there's lots of examples in our notebooks section. We also have a read the docs site. We have some information in there, but we have a large pull request that's open right now that will significantly improve and update that documentation. So please check back there soon. Next slide, please. The primary way that users are going to interact with Solar Data Tools is through the data handler object. So as shown here, you will simply import the data handler and then load your data, your Solar data into a Pandas data frame and instantiate your data handler on that data frame. And then finally run pipeline. As I mentioned before, the standard use here is all automatic with no need to add any user configuration. The main pipeline runs the pre-processing, cleaning, and quality checks. This includes the heat map matrix embedding, sunrise, sunset estimation, again, without the need for solar position, clear day labeling, and more. After you run that pipeline, the user can then invoke other analyses such as loss factor analysis, location estimation, and more, or use the plotting functions. And with that, I think that's the end of our introduction.
Yeah, thanks everyone. So I think we will kick it over to Kirsten Perry to give a live demo of PV Analytics.
Okay. Can you all see my screen okay?
Looks good to me.
Okay, awesome. Yeah, thanks for the intro, Mike. So yeah, I am Kirsten Perry, and today I'm going to be giving a demo on the PV Analytics package with an example pipeline for an AC power data stream. So as it's already been mentioned by Kevin, PV Analytics can be used to assess the quality of systems PV data. The particular analysis that I'm going to be going over here uses PV Analytics version 0.2.0, which is currently available on PyPy, so you can just directly pip install it. And in addition to this AC power data stream that we're going to be analyzing, we have additional routines, example routines for temperature, irradiance, and wind speed available at the GitHub repo for this particular webinar. So jumping into it, a little bit of background on the system that we're going to be analyzing today. So first of all, it's going to be a power data stream, an AC power data stream from the Solar Data Prize data set, specifically system ID 2107. You can get this data from the OEDI directly in here. So you can, manually install it. And then there's a couple different ways to auto install it as well, which I think is also in the repository. You can see a satellite image of the site right here, kind of in a, agricultural area in here, fixed tilt system. So right now we've got a cell running currently to the right of this slide that is downloading all of the metadata as well as the electrical data that contains our power data streams for this particular site in here. So this is just taken, imported directly off of the repo. So you'll need to dump the data into the data folder directly in order to run this. So next up, we're going to take a look at a particular AC power data stream within this actual data set. And in this particular case, we're analyzing inverter 1. So you can see that column name, particularly from the electrical data set coming in there and visualizing this data. So it's 5-minute time frequency in there. So we set the frequency at 5 minutes for this, runs between 2018 and 2024, early 2024. You can tell the system is heavily clipped just based on that pretty serious cutoff at around 30 kilowatts for everything. So next up, we're going to do a couple of basic data checks on this particular system. And the ones that we're going to do today are checking for stale data, checking for outliers, and finding abnormal data periods. So a little bit of background on each one of these while this cell is running here to the right on this particular slide. So first of all, we want to find stale data periods, which are periods where, the data has flatlined. Obviously, this is very similar to nighttime as well as clipping periods. So we actually filter both of those two out. We create masks for it. So that power or radiance function in PV Analytics actually delineates daytime from nighttime in the mask. By looking at sensor values, essentially, and how they're changing. And then we also have a clipping mask. For this particular instance, we're using RD Tools clipping mask in here, which is currently in the process of getting updated in PV Analytics in here. And then after we take both of those masks, we also have a stale data mask function within PV Analytics. So it's in the gaps gaps Python script in here. So stale values round. So we're checking for stale values over time in there, those kind of flat lines. And we also look for negative data, which is pretty simple. Just filter out, create a mask where anything less than 0 is filtered out. And then we're going to find abnormal data periods. So this one is very specific to the NREL PV Fleets initiative. So this is just one example way to do it in here. But you can include it, or you could also omit it based on whatever you would like to do, just in the, in keeping with the overall ideology with PV Analytics. For this particular case, we filter out abnormal days, which are days where the daily minimum is greater than 10% of the daily time series mean in there. And additionally, we take out outliers. So we have a Z-score filter, as well as a bunch of additional outlier filters. I just used Z-score in here in PV Analytics because it was easy. But we take out anything that is more than 4 standard deviations away from the mean. So with that, let's take a look at what this time series looks like with those filters applied. So this is just some basic matplotlib filtering on here, or matplotlib generation for a plot, going through each one of these individual filters and rendering, based on what was found in here. So you can actually see the results of this particular thing. Mostly we just had stale data flagged on this in a couple different cases. You could tell some of the day-night mask, probably the points where it's going between nighttime and daytime to nighttime. Some of those got a little, I guess, flagged as well, that didn't get picked up with mask, which is totally fine because we want to filter everything out anyways. In here. So we've got all of those stale issues coming in off that. So we're going to filter those out and keep running this thing through here. So the next step that we're going to take here is going to be a daily completeness score check. So this particular check in PV Analytics, we're going to be using a cutoff where there needs to be at least 25% of the daily data present in order for the day to be included. And in this particular instance, just to handle nighttime values, we factor in anything that got flagged as a night period is 0. So, you know, if let's say we have an instance where like some of the nighttime values are labeled entirely as NaN in our pandas time series, then we want to, you know, count those as 0 in there so that it doesn't negatively impact our completeness masking in here. So we do this using the gap script within PV Analytics. So we have a completeness score function, which just gives you what the daily value is in terms of completeness. So a value between 0 and 1, how much data you have present as a percentage. And then also a trim incomplete function, which is a masking function. So that essentially creates a Boolean true false based on whether or not you meet a minimum completeness threshold. And you can see this minimum completeness threshold right here. And our value right here is 0.25. It's settable. So you can actually, you know, change it to whatever you would like it to be. If you're like, hey, I want to be more conservative. And only, you know, if there's less than 10% data or, you know, less than 50% data, filter out. It's whatever you choose, I guess, choose your own adventure in this regard. And you can see the results here. This time series in particular has pretty good, like data availability overall. So that red line represents that 0.25 completeness cutoff. And the one is, you know, a complete day's worth of data. So pretty much all of the days meet that minimum 0.25 threshold. So next up, we're going to be doing a time shift check here. So the reason why we have this in PV Analytics is a lot of the time, time series values or system data comes with the incorrect time zone, or there's time adrift essentially within the actual time series itself. So this function in particular is meant to catch those different issues and identify whether or not the data is in the right time zone by looking at what the model data for the supposed correct time zone is supposed to be and correcting more or less to what that value should be. So I've got the heat map for this that essentially plotted right here in Matplotlib. To give a little bit of background on this particular site, it does have daylight savings time. It is technically in the US Los Angeles area because it's in California in here. So you would expect to have that time shift in the heat map because it does have DST ranging between roughly November and March of each year. So you can kind of see that shift down. So that's, you know, very similar to what we would expect in here. But we're also going to run the time shift check just to make sure everything makes sense in terms of this. So going a little bit on here, and this is definitely going to be my most code heavy slide in here. So what we do is we get a modeled sunrise and sunset value for the particular location based on its lat and longitude coordinates. We use PVLib solar position sunrise set transit SPA function to do that. And then we take a midday point. So that midday point is meant to be the midday point between sunrise and sunset in there. So that modeled midday point, and then we're going to compare it to the measured midday point for our time series. And to do that, we've got to take a day-night masking function for this once again. This is getting called several times within here, which really proves that it's, you know, a pretty critical function in here. And we essentially find when sunrise and sunset happen. So we have a daytime function that has a get sunrise and a get sunset available in PV Analytics. And that sunrise value finds when the mask essentially turns from night, night, night to day, day, day. That, you know, that delineation between when the mask changes. And the same thing applies to sunset, except in, you know, opposite directions. So it goes day, 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 and then, you know, sunset, and then night, night, night. in there. So it finds those particular values for each day when sunrise and sunset is. And then at that point, it calculates the midday point as well for the measured data set. So it's very similar to what we're doing with modeled, except with measured. And then we aggregate up to a daily value for each one of those, and take the minutes from midnight for each one of those individual values, and pass them into a PV analytics function called shift_rupture. So this is essentially running change point detection for the Python ruptures package behind the hood. And what this is doing is calculating more or less the shift amount in here for in between the difference between measured and modeled midday. So you can actually see the results here to the graphic to your right on here. There's no, time shift issues in here. So the actual measured minus modeled midday value is coming back at 0 for everything in minutes, which is, what we want to see. It means that everything's in the right time zone and we don't need to do a correction in here, which is great. So next up, we have functions for checking for data shifts or capacity shifts within a time series. And Kevin mentioned an instance where this normally occurs in data sets where, let's say, there's an operator error and they switch the units and they forget to change the units in like their SCADA data stream along the way. This kind of check makes sure that we get everything within, the same capacity, essentially taking the longest period that is shift free so that we can run further analysis on it. So first and foremost, we take a daily aggregated mean of our power time series, and we run two different functions on it. The first one is get longest shift segment dates, which essentially finds the longest shift free period based on the PV analytics functions running underneath the hood. And then the next one is detect data shifts, which you can see right here. This is also a change point detection algorithm running on the background on this that is essentially looking at whether or not there are abrupt changes within the time series and flagging those changes in there. And the detect data shifts creates a mask where, shift days where we detect a shift are labeled as true. Everything else is labeled as false. And then longest shift segment dates is pretty self-explanatory. It gives you a list of when the dates are for the beginning and end for the longest shift free period. So in doing that, we do find a data shift within this time series. You can tell it's late 2018 in here. So this is the daily AC power, mean daily AC power over time for this particular time series found here. The different segments are represented in different colors. So first segment's in blue, second segment's in orange. The longest shift-free period for this particular case would range between that late 2018 to 2024 period. So like a lot of data still available post-shift, removal in here. And you'll actually see with this particular system 2107, there are several data shifts at the beginning of the series, and in some cases at the end of the series for all of the AC power data streams, or at least 90% of them. Both PV Analytics and Solar Data Tools, which Bennett will talk about shortly, pick up a lot of those. So in addition to filtering, PV Analytics has some additional interesting functionality that is related to assessing a system's metadata. And this is important because a lot of the time the metadata provided for systems may not be correct, and you want to doubly ensure that everything you're looking at is actually right. Because if you get, if you label something as fixed tilt and it's actually single axis tracking, that can really screw up your energy estimates. So this particular function in here is a check for mounting configuration. And what this particular function does is it looks at the envelope or the daily production profile for the power data stream after both nighttime and clipping periods have been removed. And it assesses what that profile looks like. So if it comes back as a quadratic, which is very similar for what you would expect for a fixed tilt system, labels it as fixed tilt. And then if it comes back as a quartic and it has, the two bumps at the top, gets labeled as a single axis tracking. So as we mentioned before, this particular system was labeled as a fixed tilt system. So it came back as fixed tilt, which is what we would expect. So we have that double verification that things are looking good. And then last but not least, in this particular analysis, we have a methodology for estimating azimuth and tilt for a particular system. And what this does is it looks at NSRDB data. So it takes clear sky periods from the NSRDB data for that particular location. And in this case, we've actually had it locally available right now, but we pulled everything via the pvlib.io tools get PSM free function in here. And we essentially take those clear sky periods and run them through a PV Watts model and run least squares regression against what our modeled or least squares regression against our measured power versus our model power to optimize what the azimuth and tilt would be. So think of it as, you know, changing the azimuth and tilt for the model value and getting the best fit more or less with the measured value in here. And you can see this process illustrated right here. This system, as a heads up, its ground truth values are labeled as 180 degrees for azimuth and 25 degrees for tilt. What comes back from this function is 175 degrees for azimuth and 28 degrees for tilt. And we actually did a study on this with Bennett Myers because he has a similar function in Solar Data Tools as well. And last year for PVSC, and I generally found that the margin of error for most of this is about 5 degrees for the particular PV analytics function here. So that acts as a double assurance that, you know, we're getting very close to what we would expect in there, and there's nothing that's a smoking gun, essentially. And with that, I want to thank you for your time. And for any additional examples, check out our documentation as well as any of the Jupyter notebooks that we provide in our webinar today. Thanks. I'm going to hand it over to Mike now for RD Tools.
Yeah, thanks, Kirsten. That was awesome. So I will share a similar RD Tools notebook. And just as again, let's see. That's what I want to share. As Kirsten mentioned, and as Carly mentioned in the chat, all these notebooks will be available to you after the webinar. So don't feel like you need to jot down every line of code that we're sharing today. So on to RD Tools. So Kirsten just walked us through beautiful, like how to do QA, but let's just for illustrative purposes, imagine that we didn't do QA first and see what we get, because it'll, I think, illustrate the importance of the QA. Spoiler alert. All right, so first code here is just going to import the data from, again, that system 2107. So it's just going to import and parse that. I've downloaded it straight from the web interface into this directory. Should only take a moment to run. All right, so we've got that data. Let's look at how to get that into RD Tools. So again, we're going to be working with the trend analysis workflow, which you can find in the analysis chains submodule of RD Tools. In addition to the example that I'm going through today, if you look on our docs, there's another example notebook that shows how to use the object and kind of what you can do with it. So you're welcome to check that out as well. So let's look at actually how to set it up. And before I dive into that, I want to note, if you're in Jupyter Notebooks, you can hit Shift Tab and get into the doc string. And we've really tried to lay out nicely all the parameters for all these functions and classes so that you have that as a reference. So you can always get this kind of context help throughout RD Tools. I'm not going to read that to you today. So let's look at it. So we're going to set up rdtools.trendanalysis. This is a Python class, and we're going to save it as the object TA to keep working with it. Today, I'm going to give it the power time series, just looking at inverter 1 for sake of simplicity here. The irradiance, the plane of array irradiance that was reported for the site, the ambient temperature with a little bit of math to convert from Fahrenheit to Celsius, the temperature coefficient for the modules that I looked up. You can find the module number in the metadata, and then you can Google the spec sheet. So that's where that came from. And then the wind speed. Then we got to give it a temperature model so that RD Tools knows how to calculate a module temperature from the ambient temperature. And this is an open rack system with a polymer back sheet. So this is the appropriate temperature model there. So that sets up the object, and then we can deploy the analysis by just calling the method on that object sensor analysis. And year on year is the name of our degradation algorithm, the year on year approach. And so we're going to give that one argument, just the confidence level. I'm going to crank that up to 95 for today. So I'll start this off, and then finally, a method on our trend analysis object is to generate this nice plot. So what you're looking at is in blue is the normalized energy. Black is our estimate of the degradation rate from that year-on-year method. And it looks not great because there's a big data shift at the outset. So over here on the right is kind of the summary statistics. The degradation rate is positive, which would tell us that in this framework that the system is improving over time. But really, we think it's just from those teething issues in the first year. So that illustrates the importance of doing the QA. So let's try it again with the data that Kirsten has hooked us up with from the PV Analytics QA. So now I'm going to read in just some pickle files, some pandas pickle files that have that nice QA data, and plug them into trend analysis the same way. Now, as a quick note, one thing that we've really done a lot of work in RD Tools is you don't have to worry too much about making sure your time series are aligned with one another as far as frequency or just that time index. So they can be like staggered, doesn't have to be regular. I think in this case, Kirsten discovered that the temperature and the wind speed are hourly, and so we've downsampled that to hourly. So I'm feeding it with like 5 or 15 minute power data, but only hourly wind data. That's all going to get handled under the hood. So you don't have to worry too much about that. Same syntax as before, just with that QA data. Let's take a look at our result. So this is much more believable. It passes kind of our high level scrutiny. You can see we're getting here a degradation rate of about 0.7% per year. And then the 95% confidence interval between a whole percent per year and about 0.4% per year. So somewhere in that range is what we think we are seeing. I want to, so scrolling I don't think is going to work for me today. So sorry, folks, I'm going to zoom out. I want to know, like, so far I've just showed you these plots, but all the results are there in number form, so you can work with them programmatically as well. There's an attribute on our trend analysis object called results. And that is a nested dict of kind of everything that was computed so far on that trend analysis object. So you can dig in there and work with those results programmatically, save them somewhere else, do whatever you want. In this case, you can quickly see the year-on-year degradation result, our P50 degradation rates, what we print on the chart, and then our confidence interval as well. And then there's more there for you to dig into if you want. Let's zoom back to normal and continue. So there, I showed you the workflow before, right? We normalize, and then we filter, and then we aggregate, and then we analyze. And there's a lot of devils in the details when it comes to filtering. And the interface for filtering in RD Tools is also a little tricky. So I wanted to make sure to take some time today to look at that. So again, I will highlight our handy dandy doc strings. Let's look at the doc string for the trend analysis class quickly. I'm just going to comment that out because it's not going to work, but we can look at I guess I got scroll bars here. Never know with this. All right, so if you scroll all the way down to attributes, it's actually not a parameter, but it's an attribute that we're going to modify on the trend analysis class to interact with the filters. So it's detailed here, but I'm going to talk you through it live. So let's look at that attribute, which is, again, this is our trend analysis object we've been working with, the filter params attribute. What you see is it's a dict, a nested dict. Each key in this dict is the name of a function from our filtering module. So you can go back to our filtering module and look at the parameters that it would take. And any parameters that you want to modify from the default, you'd put here in this dict that is the value of that key. I'll illustrate, I'll make a more concrete illustration for you here, but that's the interface. And so you'd modify this before you run the actual year-on-year or soiling analysis to change the filtering behavior. So let's look at how it actually looks to modify that. And we've got a nice built-in Plotly plot that can help you visualize it. So in our filtering module, we've got a tune filter plot. So let's look at that. That's going to pull up a Plotly plot that allows you, and Plotly plots can be resource intensive if you do like 10 years of 15-minute data. So we're going to look at a week here just to see what's going on. And if I can get my magnifying glass, we can zoom in on the first day. So the system is clipping, right? It's got a high DC to AC ratio and definitely clips during some parts of the year. Now, if you want to assess DC degradation, it's best to remove clipping before you aggregate, because clipping will tend to mask DC degradation. If on the other hand, you want to know kind of just how the system output is evolving over time on the AC side, you might leave clipping in. So our choices in filtering are really important as to like kind of what question we're answering. And so the default is to filter clipping out as we've done here, but let's check in also on the performance of it. So we can zoom in on a peak here on the first day, and you see that some of these values kind of on the shoulder are getting filtered out by our default filter, which isn't spectacular, right? All of the whole story is told by the shoulders of this plot as far as degradation. So let's see if we can modify it to keep that in. And we're going to zoom out. Okay, so we're going to change. So I've got my filter params attribute. I'm going to change the clip filter entry in there to have the parameters models equal logic. So you would, if you didn't know what to do with that, or like what your options were, you'd be looking in the docs and the filtering module to figure out what the options are. We're going to use the logic filter instead of the default, which is called the quantile filter. And then I'm going to rerun the analysis just as we've been doing it before on that trend analysis object. All right, we've got a warning here, and this brings up an important point. So this says that the logic filter is experimental and under development, and it might change your answers. So this is an important point. In RD tools, we use semantic versioning, which means we're not going to change any of your answers as long as we don't change the major version number of RD tools. So if we go from RD tools 2 to RD tools 3, your answers are subject to change. But if we're going from RD tools 2.1 to 2.2, that's just adding new features, and we shouldn't be changing your answers, with the exception of things that we've applied this warning to. So that gives us kind of some ability to compromise and build in new functionality that maybe is not totally ironed out, or we may want to adjust the default behavior of, allows us to roll that out faster and not kind of get bogged down. So, pay attention to those warnings, but you're still welcome to use these functions. So let's see. I was going to do something else here. I wanted to run our Plotly plot again. So I've rerun things now with this new clipping filter. Let's zoom in and see how it changed things. So you see it's leaving a couple more things in on the clipped plateau, but it's letting stuff in off the shoulder. So we're about to turn the clipping filter off, so we don't need to worry about too much about tuning it. But now you've seen how to do that. So as I mentioned, we can also turn any filter off completely. And the way you do that is to remove that key from your filter params attribute. So I can use the pop method, which is just a built-in dict method in Python. Now, if we look at our filter parameters, you see clipping filter is no longer there. I can rerun our analysis. I think the result's going to be here on the next slide. We'll just look at that same plot we've been looking at before. Here you go. So if you were taking close notes, you wrote down probably that our degradation rate was in the neighborhood of 0.7, 0.8, and now our degradation rate's in the neighborhood of 0.44. So the degradation rate has slowed, which is to be expected, right? That's the physical thing that we expect to happen. If we consider the effect of filtering, it tempers the DC side degradation when we look at the AC side. Now we're looking at the AC side. So that's a nice intuitive result. And you've also seen how to modify the filters. And there's an explanation of what I just said. So far, we've just looked at degradation, but I promised that we'd look at soiling. So let's dive into that as well. So using our same trend analysis object that I've already set up and already ran, we can modify the analysis parameter to, in addition to including our year-on-year degradation, we can do our stochastic rate and recovery soiling analysis, which is what the name of the algorithm. You can read the docs. They've got it's got links to all of our papers about that if you really want to understand the details of that method. And then similarly, I can give some keyword arguments to the stochastic rate and recovery algorithm. I want to do it with 95% confidence. So let's run that. It's going to take a moment longer because doing some more analysis. All right, so we've got similar warnings that we saw before, right? Soiling module is also experimental. We're gonna lock that down for you, hopefully in the release of RDTools 3 coming later this year. But for now, we think that maybe some of the default parameters might change. So we do have that experimental warning applied here. The other warning that you see is 20% or more of the daily data is assigned to invalid soiling intervals. So the soiling algorithm is looking for this kind of Kimber model sawtooth soiling effect. And in some times of the year, there may not be a clear sawtooth signal, at least not that the algorithm can pick up. And so if more than 20% of the data falls in those times when we're not really seeing that clear sawtooth, it's going to raise this warning. So it's important to consider, and you can read through some of the suggestions and implications of it in more detail. But for today, we're going to power on because I have already looked at the results and I think it's okay to power on. So as before, in addition to the plots that we can make, again, the results attribute saves some of our important parameters, or like the result important run parameters, things that we have extracted during the analysis. So I'm going to give myself a couple of handles to those. That's all this is doing. And we can look at the stochastic rate and recovery results. It's a nested dict of everything that's come up, but we've got some plotting functions to help you make sense of it. So we've got the P50 soiling ratio, our soiling confidence interval on the soiling ratio, and then a whole bunch of other stuff. I won't have to get into all the details. I just wanted to let you know that it's there for you to dig into if you want. Okay, so one thing that I do want to highlight from that attribute is the soiling interval summary. So this is going to summarize, and this is how you dig it out of that nested dict. This is going to summarize all of those sawtooth soiling intervals that we found over the course of the data set. And it's got their soiling rate, kind of the confidence interval on the soiling rate, some details about the intercept, how long it was, start and end dates. So that's important, and we're going to actually use it later to visualize. So we've got a built-in plot soiling intervals plot to visualize those same soiling intervals that I just showed you in tabular form. Now here's our plot of our daily normalized energy, and in orange, we've got our soiling intervals highlighted. Okay, you can also, instead of looking at them in kind of the time projection, you can just look at them in terms of a histogram of the daily soiling rate. So that's available. Now, when it comes to soiling ratio, under the hood in the stochastic rate and recovery algorithm is a Monte Carlo analysis. And we can actually visualize the realizations of that analysis in RDTools. This takes a minute because it's going to generate 500 profiles. So instead of just highlighting every interval, now this is kind of like a probability cloud of the soiling ratio on every day over the whole course of the data set. So that gives you a sense for how dirty the system is and how much energy you might be losing. Finally, when it comes to soiling, some of you may already be familiar with our the NREL soiling map. We've got over 250 sites on this map where we provide these kind of statistics, monthly soiling rates and annual soiling ratios. And these were taken straight out of RD Tools, and I'll show you how to calculate them on your own systems or the Data Bounty Prize data now. So the first thing we'll look at is the soiling rate. Okay, so if we think of our sawtooth, this is just the instantaneous rate. It doesn't tell us anything about the length of time, the length of those soiling intervals, or how effective cleaning is. And it doesn't directly map to how much energy you've lost, right? You've got to couple that with information about how frequently and effective cleaning happens. But it is a really useful parameter for modeling, and so it's important to extract. So we've got a routine that's in the soiling module, and you can feed it that interval summary that we set aside before. And it's going to give you results that look, let's see here, really similar to what I just showed you on the soiling map, right? Month, the soiling rate for that month, and the confidence interval. And so this is looking over the many years in the data set and saying how many soiling intervals touched every month. And based on the statistics and the statistics of those fits, what do I think the soiling rate in that month is, and what does the confidence interval look like? It also tells you how many intervals touched that month over the course of the data set, right? So we probably have less confidence in what's going on in February than we do about what's going on in September, for example, for this site, where we've got 6 intervals touching over the course of the data set. Now we can also calculate the soiling ratio. So instead of just the rate, like I showed you before, the ratio actually tells you how dirty is my system, how much energy am I losing. And so we can calculate that on an annualized basis over the course of the data set. And so you get every year, the average soiling ratio over the course of the year, and the confidence interval on it based on the Monte Carlo that we looked at before. All right, so that wraps it up for soiling. One last thing before I turn over to Solar Data Tools, I want to look at what happens when we swap in irradiance data. So to everything I've showed you so far, we've used on-site measured irradiance data, but you can also use satellite irradiance data. So I'm going to use NSRDB, which is NREL's free satellite data product. I've got a bunch of code here that imports some files that I pre-downloaded and transposes them to plane of array. So you're welcome to inspect that later, but I don't have time to go through it. So I've generated a plane of array irradiance for NSRDB is all you need to know at this point. And to use it in our trend analysis workflow, all we have to do is pass it in as for the irradiance argument instead of using that on-site irradiance. And again, I don't have to worry about the frequencies not matching up. This is whatever it is, 5 or 15 minute. NSRDB is half hourly, I think, for this one. So that's all going to be handled under the hood in RD Tools. But let's take a look at what our result looks like. All right, that is way different than what we saw before. Earlier, we were seeing something in the neighborhood of 0.5% degradation per year. And now we're seeing something that's basically negligible. 0.1 with a huge confidence interval that spans 0. That I would say is like no degradation. So this is using satellite data is a really important check that we like to do. It's very common in commercially operated systems for irradiance sensors to drift over time or recalibration, get recalibrated, and maybe we don't necessarily have visibility of that in the time series data. And so when we see a mismatch between the degradation rate that we find with the sensor and the degradation rate that we find when we pipe in satellite data, that raises the flag that maybe take the sensor results with a grain of salt, dig in deeper, figure out if there's something going on with the on-site irradiance. I actually did this over all the inverters, and here's a scatter plot of the result that I found. You can see the degradation rate when I was using NSRDB data is clearly systematically biased from the degradation rate when we were using the sensor irradiance data. And so again, that just raises the flag. There's likely some drift or recalibration going on with the sensor over time that's affecting our ability to normalize to it. So that's an important check that we do in RD Tools. And that, I think, is my last slide. I will turn it over to Bennett to talk about solar data tools.
Do we have Kevin in availability analysis first?
Oh,
Yeah,
I'm
well,
sorry.
One more bit
Kevin,
of RD tools
availability
first.
analysis.
I'll try to get through this pretty quick here. So just real quickly, we're going to do a demo of the availability capabilities in RD tools. So I'm going to skip over the beginning here because it's basically what we've already seen, importing data, selecting out the columns that we need, and just jump right into it here. So what I'm showing you here on the left is each of the 24 inverters in this system. And this is a nice clear sky day. All of the inverters, as you can see, are producing more or less normally. Maybe there's a little bit of jumpiness, but no major outages for sure. And if we look over here at the right, this is looking at system production in two different ways. One of them is using the AC power as reported by the site's meter near the grid interconnection. And that's shown in orange. And the other is calculated by summing up all of the individual inverter level power measurements. And that's shown in blue. And you can see that the summed inverter powers read slightly higher than the meter power. This is pretty typical. If you think about it, the inverters are upstream in a sense of the meter, and there's going to be wiring losses and transformer core losses between the two. So it's pretty standard to see the meter read a little bit lower than your summed inverter powers. But if we look at another example day, here again is nice and clear sky. Maybe one inverter has a few strings offline, but there's another inverter that is ostensibly completely offline the entire day, or at least that's what the data would have you believe. But if we look over here again at the system level measurements, now we see that the situation is reversed, where the meter is reading higher than the summed inverter powers. And so somehow the meter knows about some power that the inverters don't. And what this suggests is that this inverter that's reporting to be offline is not actually offline, and this is just a data artifact like I was talking about earlier. So this is one of the problems that RD Tools solves for you is detecting this kind of problem with the data and still calculating reliable availability statistics even in the face of this kind of issue. So let's just jump right into what the actual code looks like for this. Similar to trend analysis, encapsulating all of the workflow for soiling and degradation, we have an availability analysis class that performs the availability. And I just want to very briefly mention that, in fact, the RD Tools availability analysis performs two separate stages of looking at the data and distinguishing communications interruptions from true production outages. Today, we're just going to be talking about the first one, but if you're interested in both, I encourage you to go and look at our documentation. So it's pretty simple to use. You just extract your inverter power and your meter power data and pass that into the availability analysis. And here I'm telling it to calculate daily statistics. So in this dummy example, I'm just giving it 3 days of data so that we can look at some nice plots and get an intuition for what's going on. You can set this to monthly for monthly reporting style calculations, annual or whatever frequency you want. So when we run that, one of the main outputs is this results data frame, and it's got 3 columns. One is an estimate of the lost production for each day, in this case, because I specified daily statistics. We also have the actual production of the system, and then availability, which is an energy weighted uptime ratio calculated from these first 2 columns. One thing I want to mention here is that, so these are the 3 days we analyzed. On the top is the inverter reported power data, and on the bottom is the estimated power loss. And you can see that the estimated power loss is coincident in time with the outages apparent in the inverter level data. And so this is important to get the timing right in case you have time of day delivery rates or you want to calculate revenue loss because of availability. Getting the timing correct is important. It also reflects the number of inverters being offline and the operating conditions. And so you can see there's spikiness in the estimated loss due to clouds passing over the system. That poor solar resource gets transferred into the loss estimate also. So this is a little bit of a just very whirlwind view of this. We do have a more detailed example in the RD Tools online documentation. And I'm happy to take any questions in the QA. Thanks. Bennett, over to you.
Great, thank you. Let me start sharing here. All right. Thank you all. Thank you to my presenters who came before, and thank you to the attendees who've stuck around thus far. We'll give the demonstration of solar data tools now. Again, like everything before, we are working today with the DOE Data Prize data. So do go check that out, download it, play around with it, try out these tools. So in this notebook, we're going to start with some basic software usage. And again, we're going to be looking at that same inverter 1 from the farm solar array in California that we've been talking about. We'll take a look at some of the features of solar data tools on that data set. Then we will compare and contrast our estimation of system degradation with RD tools. And then finally, we're going to take a look at a very different site called the Maui Ocean Center, which instead of a ground-mounted system is a complex roof mount system. We'll see how Solar Data Tools is able to handle both of those. So we start things off with our imports at the top, mostly standard imports. The only thing we actually need from Solar Data Tools for the whole notebook, again, is going to be this data handler right here. We're going to be using this data access and loading function. So when you get your hands on this notebook, if you have AWS command line tools set up on your machine and you use this, this will automatically go and grab the files you need from the S3 bucket, the OEDI S3 bucket. If you don't happen to have command line tools on your machine, you can just download manually, put them in the data folder, and everything should work. So we will start by loading in our electrical data for 2107. As you can see, here's all the 24 inverters we've been talking about. We have current, voltage, an AC and DC, as well as power. So with our data loaded in as a pandas data frame, we are now ready to instantiate the Solar Data Tools data handler. Looks just like this, doesn't take long. In this case, so Kirsten already mentioned this data set has daylight savings time shifts. Now Solar Data Tools has an automatic method for finding and fixing these shifts if you don't happen to know anything about time shifts in your data set. Can handle arbitrary shifts, but in this case, we know it's daylight savings, so it has a special helper function we can run that just gets rid of those daylight savings shifts right away. Having done that, we will then run the main pipeline. So all we're doing here is telling it which power column we want to run the pipeline on. As I mentioned, Solar Data Tools thinks about analyzing individual power signals in isolation, unlabeled, without the need to compare it to anything else. So on my machine with the standard run, this is going to take about 20 to 30 seconds on my machine. It's going to work itself through a little task list here. So it should be done in just a moment. There we go, 27 seconds. We'll note here that we got a little tip. If you happen to have the commercial solver MOSEC on your machine, it is an option to set that as your solver, and you will see quite a big speed up. So before we took about 27 seconds, and that took just under 4 seconds. So we've now run the main pipeline. You can see we've done pre-processing, some cleaning steps, and then some filtering and summarizing. So having done this, we can now interact with the data handler to look at our data set, understand it. The very first thing I like to do is, here we go. Oops, I did not mean to run that again, but that's okay, is run the report. So this gives us a high-level report of this data set. We can see it's just over 6 years. We have an estimated capacity direct off the data, our data sampling, a data quality score. This is a fraction of the days that do not have operational issues. We have a clearness score. This is a fraction of the days that are approximately clear sky. A flag for whether or not inverter clipping was present in this data set, and then a fraction. Again, this is a daily fraction. 26% of the days experienced some clipping. Capacity changes as well. Kirsten already talked about this. We do find capacity changes in this data set. A warning about data quality. We won't get into that right now. It's not very serious here. And then also we see that we did not find any time shift errors or time zone errors. We fixed the daylight savings ahead of time. If we hadn't fixed that, it would have found it here. We can also see this in machine readable form. So just by modifying the report function, asking for the return values. We can now get this back as a dictionary instead of a print statement. This is very useful for automating this analysis over many, many files or columns. So having done that, the next thing I like to do is to view the data as a heat map to get an overview of what we're looking at. So here we go. This is inverter 1 at site 2107. You can see just over 6 years of data, as I mentioned. In this heat map view, we have sequential days in the data set along the x-axis, as well as time within a day on the y-axis, going from sunrise early morning at the top to sunset at the bottom. You can see in this chart the differences between the summer months with the longer days and the winter months with the shorter days, as well as some data outages. If you look closely as well, you can see a bit of a change in the color here, and that's consistent with the capacity change that Kirsten talked about in the PV Analytics demonstration. We also found a capacity change, and each of our subroutines has at least one plotting function meant to illustrate what it's done. In this case, we can plot our capacity change analysis and see what it came up with. Sure enough, there is that capacity change that Kirsten talked about in the beginning. As I mentioned, we take a statistical signal processing approach to our quality analysis and loss factor analysis. And this is a view of the signal decomposition problem that was solved to find where this capacity change occurred. We have essentially decomposed the lighter signal in the back into a noise term, a smooth and periodic term, and a piecewise constant term. That piecewise constant term is our detector. And then we can turn that into a daily label as we showed before. There's a lot of other plotting functions available there we go. There's a lot of other plotting functions available, and I encourage you to explore and look through. If you have tab complete, you can see here we have quite a number of plotting functions to play around with. The next one I'm going to show is that I think is kind of fun is our polar transform plotting function. So given your power data set, if you know the lat long and the time zone of your timestamps, you can convert this into a polar plot that kind of shows you a sky view of your site. And so this is what that looks like for inverter 1. There's some interesting structure here in the morning, in the evening, in the winter that is likely due to some self-shading within the site. Now, when objects are causing shade, they're very clearly identifiable in this view, which is interesting. So for fun, let's load in the irradiance sensor that is associated with this site. So we're going to call that data loading function again, load in our irradiance data, which in this case was shared as a separate file. And we are going to run our pipeline on that new data handler object. Again, I've done it with MOSEC this time, just in the interest of speed for the live demo, but this will work just fine without that. And the version that will be available for you for download will not have the MOSEC flags turned on. So let's see what we got here. Very interesting. So to the east, there are clearly visible poles along the side of the site, which are shading the irradiance sensor. And turns out we can double check this and it's true. So here's our site again in Google Earth. And if we zoom up real close here, we can see, here we go, telephone poles that are running right along the east side of the site. And those are projecting themselves onto the irradiance sensor. So in this case, we happen to know lat and longitude ahead of time. That was provided in the metadata that the system provider handed in for the Solar Data Prize. But what if we needed to know that? So one of the analyses you can do with the data handler object is estimate latitude and longitude. This also does tilt and azimuth estimation as well. I'm just not showing that here. In this case, here was the actual lat long and the estimated lat long. We're roughly 72 miles from the actual location. So if I just zoom out here, you can in fact see that's the site, and 72 miles away north, that's where we estimated the location. So close enough for the purposes of approximately getting it right for modeling purposes, not close enough to actually de-anonymize the data set, which is kind of convenient. So the next thing I want to show is a bigger analysis than location estimation, and that's our loss factor analysis. So this analysis decomposes the observed energy in the system into a number of losses, including long-term degradation rate, soiling, weather, capacity changes, and outages, like system outages. So let's see how that looks now. I'm going to run this live. And what this is going to do is it's going to fit a statistical signal decomposition model that has been defined over the energy data. And it's going to refit that model a bunch of times in a Monte Carlo style and tweak some of the parameters a little bit, mask out some of the data each time. And this is going to give us our distributional estimate of the degradation rate. So right now it is working through that Monte Carlo simulation. It typically stabilizes in about 50 to 100 samples, sometimes even quicker. It will be required to take at least 20 samples before it decides that the population has stabilized, and it gives you the estimation of the degradation. 95% confidence interval on that degradation, as well as the estimate of the other loss factors. As it's working through these iterations, you can see it's giving you some feedback, telling you the number of iterations it's gone through, the total elapsed time. It's giving us the current P50, P2.5, and P97.5 estimates of the degradation rate, as well as the changes in those estimates as we go through. So we'll go ahead and let that continue on for a second. Once it's done, you get access to another object underneath your data handler called loss analysis that you can now interact with. It includes a number of plotting functions that are specific to the loss factor analysis. Okay, we can see it's done. It's given us a little report now that it's finished. Like with the data handler report, this report is available in a machine readable form as well. But here we go. We have an estimate of our degradation rate, slightly positive with a 95% confidence interval that spans 0. That should sound familiar because we saw something similar from the RD Tools analysis. It's also giving us some other information. It's telling us a total energy loss, a loss due to bulk degradation, a loss due to soiling, a loss due to capacity changes, weather, and system outages. So let's inspect a little bit and understand a bit about how these estimates were made. Oh, I guess first, well, we already saw the plot waterfall. So this just takes this information up above, puts it in a nice waterfall plot form. We can plot the decomposition. And this is our signal decomposition model of the observed daily energy data shown in green at the bottom. We have decomposed into a seasonal baseline, a linear degradation term, a soiling term that encourages sawtooth type recoveries, a piecewise constant capacity change term that's nearly identical to the one I just showed you above, and then a weather term, as well as outages are where there was essentially is where we choose not to fit the model because we don't think that it is behaving like a normal PV system on that day. Either there was no power or energy recorded, or it was distorted and didn't look like a PV signal. I'll note that this is a multiplicative decomposition model. So each of these terms multiply together to give you the green at the bottom. If you ignore the weather term, what you get is the blue at the bottom. So that kind of gives you a visualization of the temporal effects that we are fitting in the data. Okay, so that's our decomposition model. Now let's compare to RD Tools. So we can take our estimate that we just got out of Solar Data Tools with its P95s, and we can compare that to 2 of the answers we got from Mike's results. Well, I think I stuck with the DC one here, Mike, instead of the AC, but I meant to update this one to the AC analysis, but this is looking at the very original one that Mike showed, which is essentially removing the clipped times from the inverter and looking at it with the ground-based analysis. So here's that value that was around 0.7 plus or minus. And then when Mike looked at the NSRDB analysis, we got something closer to 0 that spanned it. And when we look at it with solar data tools, this is the uncertain we get on the left. Again, with solar data tools, this is, we're not referencing an on-site irradiance sensor. We're not actually removing any of the clipped times. We've observed that there was clipping, but we didn't affect the analysis at all. So this is going to be somewhat similar to the RD tools AC analysis. So having done that, I would like to switch gears and look at a different site. It looks very different than the one we looked at. This is another solar data bounty prize site, and this is 2105. There we go, not 2015, 2105 Maui Ocean Center. And this is a rooftop site with a lot of multi-pitch rooftops. It's a very complex system. There are a number of inverters at this site, but the metadata didn't have any clear indication of which inverters represented which or connected to which modules electrically in the field. So it would be quite difficult to put together a standard system model for this site. So let's take a look at what we can do. Again, we will load in our data. As before, this is in the OEDI Data Lake S3 bucket, Solar Data Prize, and then we're in site 2105. And I'm going to look at inverter 9, just for fun. There's a number of inverters here, but we're going to look at 9. Having loaded it in, we can again run our pipeline. In the interest of time, I have asked for the MOSEC version to get it done in just a few seconds. Here we go. We have run our pre-processing, cleaning, filtering, and summarizing. We can inspect our report. This data set has only 4.4 years. It's also a 5-minute data set. The data quality score is quite high, but the clearness score is much lower than we saw before. So our clearness score for the previous site in California was around 50%. Now this is 15%, a lot more weather at this site. We still have clipping. Let's take a look at what this site data looks like. Here we have the raw heat maps. This is without any data filling operations. The white spaces are areas where we did not receive, there was no data in the data set. In fact, there was no timestamps for any of those times. So the algorithm has figured out where they go in the 2D array and placed the measurements that we have in the appropriate locations. You can see visually that this is a lot more cloud affected site than the previous one. You can see that by the fact that our power production time is more impacted with this kind of noisy pattern. If we go back and we compare to the previous one, we can certainly see that there are some weather affected days in California, but it's pretty common to have very clear summers at this site. Whereas down here, we can see immediately, even from the heat map view, that we've got a very different weather phenomenon going on here. We also clearly see that there's some sort of capacity change going on right in the middle of 2021. We can run our polar transform again. There's not a ton to see at this site. It doesn't appear that this particular inverter was experiencing very much shade. And then we can rerun our loss factor analysis. I will try to do this again live. It took us about a minute to run the last time I did it. So we'll let that kick off and see what it does. While it's running, we'll go ahead and skip ahead to the results I calculated right beforehand. We can view the breakdown of the loss factors. Again, I chose a different plot this time. It's got a waterfall plot as a built-in option. It's also got a pie plot as a built-in option. One difference to think about is if we're thinking about this as losses, and all the losses for a pie chart to make sense have to have the same sign. So in the previous example, we actually got a slight increase in the degradation of the system. And so the pie chart doesn't make quite as much sense in that context. We can also, again, view our decomposition model of the loss factors in this particular data set. One thing I want to note that is very interesting about this data set is the concurrent impact of both a large soiling event as well as the capacity shift and recovery that we saw here. And we can see how the statistical decomposition algorithm does a good job of separating those two effects out. Checking back in here, minute 15, so we're a little bit longer than the one I did right beforehand. That can happen sometimes with Monte Carlo. It can take a little bit more or less time to stabilize the distribution. And at the bottom, I just want to note that when I ran this straight through ahead of time, without MoSec turned on, but with all the data sets pre-downloaded, whole thing took about 3 minutes to run on my laptop, to give you a sense of how long it typically takes. So that brings me to the end of my demo. You've heard about PV Analytics, RD Tools, and Solar Data Tools today. These are 3 different free and open source Python packages available online, developed with Department of Energy funds, made for use by the research community and industry. You can see some information comparing and contrasting here. And with that, I think we will take our questions. Take your questions. Thank you.
Yeah, thanks, Bennett. Thanks, everyone. And so I think the link here at the bottom is, I think Carly is also going to put that in the chat for us, where you can access all the tutorials you saw today and go through them at your own pace. So I know a number of us have been working on some of the questions as we go. Here we've got a question. All right, Kirsten, you've tagged it. Do you want to grab it?
Yeah, I can speak to it. And I actually think this might be a good pitch too, Bennett, for the PV Validation Hub. So one of the questions we've got is all 3 tools are interesting. Some of them have the same functionalities. Are there any comparisons between tools for degradation losses or other analyses? And I'll be the first one. I guess I'll answer this question first, but I think all 3 of us can probably pitch in on this one. So to answer that, actually, Bennett and I have done a series of studies for the PV Analytics versus Solar Data Tool stuff, and I'll attach this to the chat. But we do have a comparison study for time shift analysis, which I presented at PVRW last year. And we also have one for azimuth and tilt, which was presented at PVSC last year. And a lot of the work we've been doing for the PV Validation Hub actually uses some of the curated data sets that Bennett and I have been putting together. And Bennett, do you want to pitch PV Validation Hub right now for PV Insight?
I will talk about PV Validation Hub. I also want to briefly mention that Mike and I are going to be discussing RD tools versus Solar Data Tools at this summer's PVSC. I can actually pleased to announce that as of this morning, I can say that that was accepted for an oral. So you'll hear us talking about that there. But Kirsten mentioned the PV Validation Hub. And yeah, so this is a project that Kirsten, Mike, and I are collaborating on, and we are developing a website and online tool for validating algorithms for PV data science. And what we're going to have is a number of different analytics that have been predefined, such as time shift detection, capacity change detection, degradation rate estimation, sunrise sunset estimation. A number of these things will have curated data sets for validating these algorithms, as well as well-defined scripts, methodologies for validating these algorithms. And then all kinds of users from academia, from industry can then go there. They can submit their algorithms for validation. They can get detailed reports back on how it performed with breakouts, by different parts of the data set. They'll also be included in a public leaderboard that will display high-level summaries of the performance of those submissions, including things like runtime, a top-level accuracy measurement, the amount, the data that is required, right? We talked today that these different algorithms have different data requirements as well, so that's an important consideration. And then from the leaderboard, folks that are interested in these algorithms will be able to peruse these results and then click through and see project pages, see documentation, and figure out how to get their hands on these. So that's the Validation Hub. We are currently in alpha testing of that. We've got a functional system running that can accept submissions, and we've got 2 of the analytics defined with curated data sets, and we're looking forward to getting public testers on that very soon.
Cool. I
And
think
I saw you flagged one,
Sure.
minimum number of years.
Yeah, this one I think is fairly straightforward. So there's 2 answers that I just want to specify. There's minimum number of years to have the code function without an error, and then a minimum number of years to get results that are meaningful or reliable. The answer to the first one, in terms of the way the algorithm is written, would be 365 plus 1 days. Now, I don't think you can get a very good estimate of a long-term degradation rate from 365 plus 1 days. Generally speaking, I would say approximately 3 years or more is a minimum amount of data to get results that are reliable out of this method. Though there is we can generate results that may be useful in the range of 2 to 3 years.
Cool. And I have a question here from Mark about whether there's a mechanism to mark the time series events. Like I mentioned that maybe radiant sensors can be recalibration. RD Tools does not currently have that functionality, but it's something that's interesting to think about how that might look. So thanks for raising it. I don't know if folks want to speak to the other packages and how they may or may not handle like known events.
Well, so quick answer on the Solar Data Tools side, we don't currently have the ability to add user-defined events, but we actually are inheriting known capacity change events when we run our decomposition analysis. It's actually under the hood and the user is not aware of it, but we do in fact inherit those capacity change labels that I showed at the beginning into the later loss factor analysis. And there's actually a hook. A user could add their own capacity change labels in there if they wanted. So we have that as a not a documented ability, but it's something that could be done. And we could add more hooks possibly for things like known wash events in the soiling term. Not in the model yet.
Kirsten, Kevin, is there anything in PV Analytics that comes to mind as far as flagging events?
not currently. Yeah, most of it's all automated, so we don't have an option yet that I know of for flagging events. You don't know of any either, do you, Kevin?
No, I think for PV Analytics, I mean, it's not doing any sort of long-term analysis that would span an event like that. So to whatever extent you do have events like that, you could partition your data set and just do independent analyses on each chunk.
Yeah, but interesting for us all to think about, I think, you know, especially if we like are fusing O&M data with time series data, for example, it could be interesting functionality to think about. Yeah, I think the rest of the questions are just kind of applause and comments. So we appreciate that. We appreciate everyone,
Thank you.
all the attendees for dedicating some time to join us today. Give it a minute to see if any other questions come through, but I guess we're at the end of the time too, so we should probably wrap it up.
One
So with
last thing
that,
is
Yeah,
to
go ahead.
plug the next webinar on Thursday, just to remind folks, it's going to be looking at PV modeling tools, so predicting PV power as a function of weather and things like that, rather than
Yeah.
doing the inverse like we did today.
Please make sure to get registered for that. Thanks to the Department of Energy and Solar Energy Technologies Office for making this data bounty prize happen so we can have public real world data to make these kind of awesome examples. I think it's been really exciting to work with.
And I want to thank all the lab colleagues for doing great work here, for talking about the great tools that have been developed by the labs themselves and the solar community. And we welcome everyone to take a look at the repositories and familiarize themselves with them, and hopefully in the future even contribute to them.
Yes, please, if you find any problems, you know, put a report, maybe do a pull request, fix it up for us. We'd love that.
All right. Well, thanks, everyone.
Thanks, y'all.
See you guys
Thanks,
in a couple
everybody.
days. Bye.